All right, welcome to this masterclass explainer on Bohr's atomic model. Look, today we're not just going to sit here and blindly memorize textbook formulas. We're going to approach this like true physicists. We are going to derive the absolute secrets of the atom rigorously from first principles. So if you've ever found yourself wondering where exactly those equations for atomic radius and energy actually come from, well, you are in the exact right place. Let's get into it. Here is our roadmap for today. We'll kick things off with the classical physics crisis, patch that up with Bohr's radical postulates, prove the whole thing with step-by-step mathematical derivations, map it to real-world evidence, and then finally explore the ultimate limitations of the model. Section 1, the classical physics crisis, the fall of Thomson. To truly appreciate why Bohr's model was such a massive game-changer, we first have to talk about the spectacular failure of the classical atomic models that came before him. Our story really kicks off with the famous 1909 Geiger-Marsden experiment, directed by the legendary Ernest Rutherford. Basically, they took a stream of heavy, positively charged alpha particles and fired them at a microscopic piece of gold foil. We're talking just a fraction of a micrometer thick here. They surrounded the whole setup with a luminescent screen so they could trace exactly where those particles ended up. Now, at the time, J.J. Thomson's plum pudding model was the accepted truth. People assumed the atom was just this soft, diffuse blob of positive charge. So Rutherford naturally expected his heavy, super-fast alpha particles to just punch right through, kind of like bullets through a cloud. But reality completely shocked them. Roughly 1 in 8,000 particles completely backscattered. Rutherford famously said it was like firing a 15-inch artillery shell at a piece of tissue paper and having it bounce straight back to hit you. No way, right? So, this experiment proved definitively that the atom is mostly empty space, but it has a tiny, intensely dense, positively charged nucleus right at the center. Now, to keep the negatively charged electrons from just being instantly sucked into that nucleus, Rutherford figured they must be orbiting it. Make sense? But actually, that instantly created a massive existential paradox for physics at the time. You see, the whole planetary analogy failed spectacularly because of James Clerk Maxwell's widely accepted theory of electromagnetism. According to Maxwell, any charged particle accelerating in a circular orbit must emit electromagnetic radiation. And because an orbiting electron's direction is constantly changing, it's constantly accelerating, so an orbiting electron should be continuously losing energy, slowing down, and spiraling right into the nucleus in less than a trillionth of a second. According to the rules of classical physics, matter shouldn't even exist. Section 2. Bohr's bold quantum postulates, breaking classical rules. Enter a 25-year-old Niels Bohr in 1913. He realized something profound. To fix our understanding of the atom, he couldn't just tweak classical mechanics. He literally had to break the rules. Bohr came out and asserted a truly radical patch to reality. He basically said, hey, classical electromagnetism, it simply does not apply inside the atom. He proposed instead that electrons exist in these special stationary states where they can orbit without radiating any energy whatsoever. Now, this was a massive, unproven assumption that violated everything physicists knew at the time, but it was the only thing that allowed atoms to be stable. The absolute heart of his theory comes down to this one specific mathematical postulate. The angular momentum, which we represent with an L, of an orbiting electron is strictly quantized. It can only be integer multiples of Planck's constant h divided by 2 pi. This integer, n, is the principal quantum number. Think of it like legally locking electrons into specific allowed tracks and strictly forbidding them from floating anywhere in the space between. Section 3. Deriving orbit radius and velocity, mathematical derivations. Let's mentally step up to the chalkboard here and see how this all builds, stepping through the proofs, just like you'd see in a high-level university lecture. Okay, so to find the exact radius, we start by assuming circular motion. We equate the inward pull of the electrostatic Coulomb force to the centripetal force that's required to hold the electron in its orbit. Next, we take Bohr's shiny new quantum condition for velocity and we just substitute it straight into our force equation. The velocities cancel out beautifully, and by simply isolating r with some basic algebra, boom, we've derived the exact formula for the allowed electron radii. No memorization needed. And the real beauty of deriving this equation is that we can actually test it.
When we plug in all the known constants for the very first ground state orbit, where our quantum integer n equals 1, we get 0.53 times 10 to the minus 10 meters. This specific number is known as the Bohr radius. And guess what? It perfectly matched other scientific estimates of the time. This gave Bohr incredible confidence that he was onto something huge.
We can actually derive the electron's velocity using that exact same logical flow. If we isolate velocity and substitute in our newly derived radius, we find that the electron in that innermost ground state orbit is traveling at roughly 2.18 million meters per second. That is intensely fast. We're talking about 1% the speed of light. But crucially, it's safely below the ultimate speed limit of the universe, meaning Bohr's model didn't violate Einstein's theory of relativity. Section 4, the energy of bound states, total energy. So once we have the radius and the velocity sorted out, we can finally uncover the single most important property of these quantum orbits, their total energy. But wait, before we crunch the numbers, we have to grasp the physical intuition behind a negative sign you're going to see. In physics, potential energy is defined as exactly zero at an infinite distance, basically when the electron is completely free. But because the electron is so heavily attracted to the positive nucleus, you literally have to pay energy to rip it away. Therefore, an electron trapped in an atom must exist in an energy deficit. A bound state is always a negative energy state. So, to find the total energy, we calculate the positive kinetic energy from the electron's speed, and we add the much larger negative electric potential energy from its trapped position near the nucleus. When we plug our radius and velocity variables into this sum, the constants consolidate perfectly, giving us a ground state energy of exactly negative 2.18 times 10 to the minus 18 joules. Now, taking a look at our final formulas, this cleanly summarizes our first principles derivations. And if you really want to understand this on an advanced level, notice these brilliant scaling patterns. Radius scales proportionally with n squared, meaning those orbits get much farther apart as you go outward. Velocity scales with 1 over n, meaning outer electrons move slower. And energy scales with 1 over n squared. By the way, if you swap the single hydrogen proton for a larger nucleus with atomic number Z, like a helium or lithium ion, these formulas easily adapt just by multiplying the attractive force by Z. Section 5. Decoding the emission spectrum. Bohr's physical proof. Of course, mathematical elegance means absolutely nothing without physical evidence, right? So let's look at how Bohr's equations perfectly explained a massive, real-world mystery. Bohr proposed a brilliant mechanism for how atoms emit light. When a hydrogen atom gets excited, an electron absorbs energy and jumps up to a higher, less stable orbit. But it really wants to return to the lowest possible energy ground state. As it inevitably falls back down, it emits a photon of light. The energy of that emitted photon is exactly equal to the difference between those two orbits, and that directly dictates the wavelength, or the color, of the light emitted, based on the equation E equals hf. And folks, this was the absolute smoking gun. Bohr's calculated energy jumps perfectly matched the specific wavelengths of the Balmer series, those mysterious colored lines scientists had observed but couldn't explain. By taking his theoretical energy differences, Bohr mathematically derived the empirical Rydberg equation from pure theory. He completely proved that energy quantization is real, and this stunning confirmation rightfully won him the 1922 Nobel Prize.
Section 6. Limitations and the quantum leap. The next quantum leap. Yet, as is pretty much always the case in physics, solving one giant mystery naturally unlocked a completely new set of profound, almost existential questions. When Ernest Rutherford actually read Bohr's paper, he wrote back with a brilliant critique, raising a huge alarm about cause and effect. Think about it. During a quantum jump, an electron emits a photon of exactly the right wavelength corresponding to its final destination. But Rutherford asked, how on earth does the electron essentially know where it is going before it even gets there?
Rutherford really hit the nail on the head, highlighting the cracks in the foundation. Bohr's model was a genius patch, an incredible mathematical bridge. But it was deeply mysterious because, at the end of the day, it couldn't explain why that angular momentum rule existed in nature, nor could it detail the actual physical mechanism of these sudden quantum jumps. Furthermore, while it worked absolutely perfectly for hydrogen, the math completely fell apart the second you tried to predict the spectra of atoms with more than one electron. Bohr boldly brought the quantum world into the atom, but he still clung to those classical planetary orbits. So we are left with a massive question. Does the electron actually travel in a perfect circle like a tiny moon, or does it dissolve into a weird cloud of pure probability?
The true answer to that question would have to wait nearly a decade for Schrödinger and Heisenberg. But hey, that is an explainer for another day.
Okay, let's jump straight into this explainer by validating a major frustration. If you've ever sat through a chemistry class, you know exactly what I'm talking about. That massive, glaring disconnect between the simple, static little diagrams of atoms in your textbook and the totally bizarre, dynamic reality of quantum mechanics. We get handed these strict rules about where electrons can and can't go, but the actual physical why completely gets lost in translation.
So, welcome to today's explainer. We're diving deep to answer a question that literally drove physicists insane for over a century. What does an atom actually look like? Look, it's totally fair to be confused when page 1 of a book shows you a neat little planetary orbit and the next page shows you fuzzy clouds, balloons, or these weird rainbow-colored donuts. Today we're ditching the cartoons and uncovering the real physical and mathematical reality of the atom.
All right, real quick, here is our roadmap for today. 1. The planetary model fails. 2. Electrons as standing waves. 3. Decoding the quantum numbers. 4. Dynamic orbitals and probability. 5. Rules of electron configuration. And 6. Valence shells and ions.
Let's kick things off with Section 1. The planetary model fails. The classical physics crisis. To understand where we are, we have to trace this incredibly rapid historical shift. Imagine it's 1909. The accepted scientific truth was J.J. Thomson's plum pudding model. Basically, everyone got the atom was this soft, diffuse blob of positive charge. But then Ernest Rutherford comes along, fires heavy alpha particles at gold foil, and completely shatters that idea. When some of those particles bounce straight back, he realized, oh wow, the atom is almost entirely empty space with a super dense, positively charged nucleus at the center. Now, to keep the negative electrons from just getting sucked into that positive center, he assumed they must orbit it like planets around a sun. But that assumption created a massive problem, which Niels Bohr eventually had to patch up in 1913.
And here is that existential crisis. Under James Clerk Maxwell's widely accepted theory of electromagnetism, any charged particle accelerating in a circular orbit has to emit radiation and lose energy. So if an electron was actually orbiting like a planet, it would spiral into the nucleus in less than a trillionth of a second. Literally, matter shouldn't even exist. So, to fix this, Bohr just boldly broke the rules of classical physics. He proposed this quantum patch, essentially saying that electrons are locked into stationary states where classical electromagnetism just straight up doesn't apply.
Which brings us right to Section 2, electrons as standing waves. The paradigm shift. So, Bohr's math worked brilliantly for hydrogen, sure, but he actually had no idea why electrons were locked into these specific states. To grasp this, we kind of need to mentally walk through the dimensions. Every single thing in the universe has a wave-like nature. Think about clamping a one-dimensional wave, like a guitar string. It can't just vibrate however it wants, right? It's physically constrained. Step that up to 2 dimensions, like a drumhead, and the vibrations are constrained by that clamped circular boundary, creating distinct, beautiful patterns. Well, in an atom, an electron is a wave, but it's confined within a tiny 3-dimensional volume by the intense electric pull of the nucleus.
And this is the absolute core of the paradigm shift. Because the electron's wave is trapped, it becomes what we call a standing wave. It's just like how the guitar string always plays very specific, quantized tones, depending on where it's pressed down. An electron literally exists as a strict 3D standing wave vibrating around the nucleus. It is only allowed to vibrate in specific quantized modes, characterized by nodes, which are just dead spots with zero movement, and antinodes.
Let's keep moving. Section 3. Decoding the quantum numbers. Mapping the quantum geometry.
Every single electron in an atom is described by a set of 4 unique quantum numbers. If you're a chemistry student trying to figure out how atoms bond, these are basically your holy grail. Think of them as the precise coordinates that define the size, shape, orientation, and spin of our 3D standing waves. First, you have the principal number, n, which sets the overall energy level and size. Then the azimuthal number, L, which dictates the actual shape, giving us those famous s, p, d, and f orbitals based on angular momentum. The magnetic number, ml, tells us exactly how that shape is oriented in 3D space. And finally, the spin number, ms, defines the orientation of the electron's own magnetic field.
And it is so incredibly cool to see how those numbers actually translate into physical reality. We're looking at the specific, lobed shapes of the p and d orbitals here. These distinct geometries are totally dictated by angular momentum and these complex mathematical solutions called spherical harmonics. Just picture a yo-yo for a second. If it has no angular momentum, it just hangs straight down. But give it angular momentum, and it swings out. In the exact same way as those quantum numbers increase, representing higher angular momentum, the electron's wave probability fans out. It goes from being a simple little sphere into these crazy perpendicular dumbbells and four-leaf clover shapes.
Now check out the radial component, because this is where things get really fascinating. Those complex lobes we just talked about, those are defined by angular nodes. But here we are looking at radial nodes. This graph plots the distance from the nucleus against the probability of actually finding the electron. Notice those specific dips where the probability drops to absolutely zero? Those are the concentric radial shells of our standing wave. As you bump up the principal quantum number, say moving from 1s to a 2s to a 3s orbital, the wave's probability physically pushes further and further out from the nucleus.
All right, Section 4, Dynamic Orbitals and Probability. Breaking the static illusion.
Okay, because orbitals are these dynamic, living states of probability, we really have to talk about how electrons move between them. When an electron absorbs energy and jumps to a completely new quantum state, it doesn't just instantly teleport like magic. Because quantum probability is conserved, the probability actually flows through space, morphing from one geometry into the next. We call this a probability current. It's literally a deterministic fluid flow of pure probability.
I love this quote because it perfectly grounds all this weirdness. The quantum world can feel entirely absurd, completely counterintuitive to our classical brains. But the big takeaway here is that quantum mechanics is incredibly rigorous. Sure, we might not know the exact pinpoint physical location of the electron particle at any given second, but the standing wave itself, the mathematical probability of where it is, perfectly, flawlessly obeys the conservation of energy and momentum. It is a strict, entirely deterministic rulebook.
Speaking of rules, let's jump into Section 5, Rules of Electron Configuration, the Chemistry Rulebook. You see, the specific geometries and spins of these 3D standing waves mathematically force electrons to fill up the atom in a highly systematic way. When you're sitting in chemistry class trying to memorize all these principles, it really helps to remember that they aren't just arbitrary laws a teacher made up. The Aufbau principle simply states that the standing waves closest to the nucleus, the ones with the lowest energy, fill up first. Hund's rule tells us that if multiple orbitals of the exact same energy are open, electrons are going to spread out and half-fill them before they ever pair up. And then there's the big one, the Pauli exclusion principle. This dictates that absolutely no two electrons can share the exact same four quantum numbers. They can share a shape and a location, sure, but if they do, they must have opposite spins.
Let's actually look at how this plays out in practice. The checks and X's here are such a great way to visualize exactly how these rules prevent electrons from just crowding into identical quantum states. Those little arrows, they represent the electron spin. Look at the bottom. You see an X marking a spot where two up arrows are jammed into the same 1s orbital. That is a massive direct violation of Pauli's exclusion principle. Nature just won't allow it. Up top, though, you see the correct configuration. Electrons only pair up with opposite spins when they absolutely have to, which perfectly distributes their standing waves to minimize interference and keep energy as low as possible.
And finally, Section 6, Valence shells and ions, chemistry in action.
So when atoms actually interact out in the real world, they aren't just smashing their nuclei together. The inner core electrons, those super tightly bound low-energy standing waves we just talked about, they honestly just ignore the outside world. It's the outermost waves, what we call the valence shell electrons, that are highly energetic and fully exposed. These specific valence electrons are the sole drivers of chemical bonding, molecular structure, and literally all the chemistry happening around us. And this perfectly explains why atoms are so desperate for chemical stability. Take an alkali metal, like sodium, for example. They are notoriously highly reactive. Why? Because they have just one lonely, totally unpaired valence electron sitting out in an outer spherical s orbital. It's a completely electronically unstable standing wave. So, to achieve harmony, the atom will actively ditch that electron, becoming a positively charged cation. By shedding that dead weight, its new outermost shell is completely full and satisfied. It becomes isoelectronic with the nearest noble gas, basically achieving this beautifully balanced, perfectly spherically symmetric standing wave. That relentless quest for quantum stability, that is exactly what makes the entire universe tick.
Which wraps up our explainer for today, but I want to leave you with one final thought. We started this journey looking at tiny, literal solar systems and ended up diving into mathematical probability currents. So,
What actually is the atom? Well, it's not a classical bouncing particle, and it's definitely not just a simple ocean wave. It is this incredibly beautiful, dynamic, deterministic fluid of pure probability, totally constrained by the fundamental geometry of the universe. So next time you stare at a periodic table or try to balance a chemical equation, I really invite you to see past those basic textbook letters. Try to picture the universe for what it really is: a magnificent, infinitely complex symphony of quantum standing waves. Thanks so much for learning with me today.